Hello everyone, November 26th. Alright, just get off work. Let's get this done. Shortest distance after something. After row addition queries. 1. You're given integer n and a 2D integer array queries. There are n cities, number from 0 to n-1. Initially there is a unidirectional road. Unidirectional road from city I, where is I? City I to city I plus 1 for all the i's. Okay? Queries represents the addition of a new unidirectional road from U to V. After each query, you need to find the length of the shortest path from city 0 to city n-1. Return an array answer where for each I in the range of the queries, answer I is the length of the shortest path from 0 to n-1 after processing the first I plus 1 queries. Okay, so in this case, the shortest distance, from if without any queries, right, without any this. So basically what it does, and also accumulates, right? Accumulates. So in this case, it's 3. You have 1, 2, and 3. In this case, you add a 0 to 2, and you can do 0 to 2 and 2 to 4, right? And in this case, you can go directly 0 to 4. Okay. So second example, 1, and this added, that does not matter. Okay, n is 500, query is 500. There are no repeated rows among the queries. Okay, so what we have is added rows, right? And we need to use the previous kind of to help with future. Otherwise, you have to recalculate every single time. And for each query, we can run for each query, right, you can do a BFS, right? A BFS will find, and BFS will take, ON, and you do this OMN. So naive solution is OMN. So each one you have to redo. And of course, this is going to time out because it's 500. 500 times 500 is definitely going to time out. Even if it doesn't, I feel like this is not the smart way. The smart way is definitely if we can record the previous state, right? Record the previous state. Let's say we have found the shortest path, right? So at the beginning, the shortest path is just this, right? To 3 and to 4. This is the initial shortest path. Let's say we find it, okay? And then we say we can add a query. And the query can be connecting anything, right? If we add a query, so we know we have from a certain point, right? So in this case, it's from 2 to 4. We add this. So we can say initially from 2 to 4, what's the shortest path? So basically it's just, okay, I want to know the shortest path. Let's say we have an array, okay? So I have 0, 1, 2, 3, and 4. So the shortest path to reach is 0, 1, 2, 3, 4. This is how we start. This is the starting state, right? And then we say we add a 2 to 4. So what I look at is, I look at 2, okay? Currently, 2 to 4, there's 2. And I'm adding this, so we can say, okay, let's try it. Let's try from 2 to 4, okay? And then we see what will be the shortest path. So 2 to 4, so I look at the shortest path for 4 is going to be 0. So after adding, this is going to be 1, right? This is going to be 1. So we have a new state, right? This is the new state. So this is going to be 1 because this is 0, so it can be 1. And because this changes, everybody has a change. Now that I am not quite sure. I'm not quite sure because this have to change, and then you report 3, right? But you have to kind of change backwards. Change backwards. And you have to make the change because you're basing on this, right? You're basing on this. So basically, it's still O because you have to go through every single one, and you have to go through every single time. So OMN. It's still OMN, I feel like. Yeah, next is the 0 to 2. So I say from 0 to 2, the shortest path is 1, so this becomes 2. Right, so this becomes 2. And the next is 0 to 4, and this becomes 1. So yeah, we can do it that way, but you have to update these things, right? How is there a faster way to do this update? I feel like, I mean, is this something that a binary index tree can do? So if I remember right, binary index tree can handle prefix sum, right? And you're saying when you update a value, you add something, you add to, so prefix sum, you add something to the current, and all the ones like behind you, they got updated, right? That's kind of a prefix tree. So this, maybe we can do some, because it's the same, right? You're changing something, and everybody in front of you has to be updated. It's the same, like if it's binary index tree, we have a prefix sum. So if you add this, if you add 1 for this, and everybody after you have to add 1, right? So you have 1, 2, 3, and then it'd be 1, 3, 6. That's the prefix sum. So if you add 1, so this, if you add 1 to this, and this has to be 7, like 6 had to add 1, right? So it's the same idea that you just minus 1, and everybody to the left has to minus 1. We can rotate it, we can do it. I think binary index tree can do it, definitely, but I doubt that it will require a lot of effort, so I'm not quite sure if I want to do it. So I think I will just go with a naive solution. Not this is not really the naive solution. The naive solution is redo the I think the naive solution is redo the BFS every single time. But this one is, I think, slightly better. All right, slightly better. So we can say, we call it DP. All right, new int should be n. So dpi is equal to minimum distance from I to I minus 1. Okay. All right, and we'll say for int I equal to 0, I smaller than n, I plus plus. We can say dpi shall equal to n minus I minus 1. I believe that is, yeah, because n is 5 minus, yeah. So we set it up, and then we say int res new int queries dot length. Okay. For int I equal to 0, I smaller than queries dot length, I plus plus. All right. So what we have is the query I from this to this. So what I want to know is, so int u is queries 0, right? And int v is queries 1. So we have u to v, okay? So from v, I know it's smallest distance. So basically we'll say if, right, if dp u no, if dpv plus 1, right, because dpv is the minimum, and we plus 1 from u to, if this is smaller than dpu, okay, then we shall say wait, do we need to update? That's actually a good question. Do we need to update? We absolutely do, because actually I am not quite sure. I think there is, like in here, you do have to go back because this is the previous. You need to know the previous, the shortest path previous, because what can happen is you add a link and then from this you add a link, right? So when this changes, anything in between does not change, right? Like this is shortest path still going through here, right? But you need to go from here to know its parent. You also need to know the parent and then go through the parent. Yeah, basically what it means is if I have, like say, if I go from 2 to 3, if like we go one way, right, and then we add another one that can make it even better. Now when we can make it even better, and then we have this, so we don't go through anything in between because they don't really care. I just go from here directly to the start, right? Directly to the start because that's the shortest path. And if you go through the other way, then if you go through the other way, how do I update? That's actually a question, right? Like you have some previous node, you don't know how they go, right? You don't know how they go, but this node, right, I get its distance dropped. So anybody that depends on this, they shall change as well, right? And anyone that depends on this needs to change. All right, so like this one depends on, but if I go here, so if this one drops, this one needs to change, and this one needs to change as well. Oh, that is not good. I can have a lot of updates. Right? We're gonna have a lot of updates if we do it this way. Yeah, then you need to know who's your parent. Like which one can get you to the shortest, right? Because you have changed. Actually, no, not just that. I think it's everybody, right? You have to update everybody. But do I need to get to everybody? That's actually a good question. Do I need to get to everybody? Well, I think you only need to get to the shortest distance, right? So something changes, and then the shortest distance gets changed. What do you mean by shortest distance? Shortest distance means from this node, its shortest distance. Yeah, the next step that can lead it to the shortest distance, right? And the next node, we're gonna say the next stop, right? The next stop. Next city, right? Next city. So, and then next city I'll update, and next city we will update. We have to go like backwards every single time. Next city need to update, next city need to update, next city need to update, next city need to update. And then next city. So now if 0 is to 2, right? We add this. And if the new roads that has been added, then we shall say the next city that leads you to is going to be that, right? That leads, we're going to update the next city, which means in the future, if we come to you, because this is like your current shortest distance from this to this, right, gives you the shortest distance. And in the future, what if you go through another one can give you shortest distance? Exactly, right? Exactly. That's my problem. That's my problem. I don't know how to best represent this. I feel like it's gonna cause error. Because if you only look at the shortest distance from each node, I mean, you should, right? You should. But when you update it, when you add a new, yeah, I can imagine if, like this, right? You have, I don't know, just kind of randomly drawing something. If I add, let's say, this path, okay? I mean, of course, you have all the small paths. If I add this path, then, of course, this give you shorter, right? But in the future, if I get this, right, then this is shortest. But when I do, like if I do this, I know, okay, from this to this, I only need one. Then I go back here, and I need to update its, right, current. And its current is going through here, right? Its current is going through here. And, right, its current is going through here. And if I use this and this does not concern, then this one will not get updated, right? It's not getting updated by this. You have to like literally go in here and then see if you go through here, what's gonna be. If you go through your original, so I have original, right? And then you go through here, what's gonna be, right? But what if I have some nodes, like we have other nodes in between, and then you don't go this way, you also can go this way, right? If I have this road, right, you can go this way. And if you go this way, then like how do you know whether which way you need to go? What if I have multiple? So every one of them need to get updated. That's true. Every one of them need to get updated. So for you need to keep track of who comes to you. So when you change, that whoever connects to you need to be changed, right? And then you have go here, whoever comes to you need to be changed. Well, it's just like every single time you have to do this. And this does not seem to be any simpler compared to if we just run BFS every single time. And the difficulty of BFS is simply just we need to update this the graph. But we can definitely do the graph, right? Yeah, I think I changed my mind. I'm gonna still go with a naive solution, but I'm still thinking maybe there is a way, to make this simpler. Now, how do we make this simpler? How do we know that, certain steps is going to perform better than the others? Or like, is it really the previous state can help the second of the future state? If I know how the path is, the previous one, now I add a new path. Can I use this knowledge? Can I use this knowledge? Because what you're saying right now is you cannot use the previous knowledge. Now the previous knowledge is just the previous shortest path. What I'm saying is the previous shortest path cannot help because, again, I'm using this example. This is the previous shortest path, right? So you go this, and then you jump, and then you go down. This is the previous shortest path. But this one will not help if I add a route like this. If I add a route like this, the previous shortest path completely need to be destroyed. You cannot use that at all. You have to rebuild, right? You have to rebuild. Like, this path has been abandoned in the previous shortest path. But if we add this, then this path needs to be added back. Therefore, I think I changed my mind. I'm going to go with the naive solution of we're going to use a map to keep track of, who can you reach, and then every single time we just run BFS. Yeah, it's not going to be ideal, for sure. It's definitely not going to be ideal, but I don't know. I feel like that's the only way. All right, doesn't matter. So we're gonna do it at least. Okay, we're gonna call this. This is gonna be a graph, new hash map. Okay, and then and then we need to do the original one, right? For int I 0, I smaller than n, I plus plus, right? So the original graph is gonna be graph dot put I new array list, right? Array list, and then graph dot get I dot add I plus 1. Of course, this actually should be -1 because the last one is not included. All right, so we go through this, and then we have int res new int queries dot length. Okay, and for int I 0, I smaller than query dot length I plus plus, what I'm gonna do is we'll call a function called our shortest path. We'll call it BFS. Okay, so we call BFS, we'll pass the graph, and well, we first need to update the graph. So graph dot get actually let's put everybody. Is it allowed? Actually, I'm not sure. Turn 1, turn. I'm not sure because I want to try something. Can I do a 4 to 4? Curious. Oh, I think it should be less. Yep, so they cannot do a self. That is fine. I have no, so we can just say graph dot get, queries I 0 dot add queries I 1, right? We add this, and then we're gonna say res I equal to BFS graph, or we can call it shortest dist graph, and then we'll return res. All right, so this is how it's gonna be, and then we're gonna have a private int shortest dist, and then we'll pass in the map integer call it graph. Okay. All right, so what's your brilliant idea? Well, the brilliant idea is we're gonna use a deck of int q. I think it's called array deck. Yep. And then q dot add new int. It's always gonna be, we start from 0 with 0 steps, right? And and then we have to have a target. Okay. And then while q dot is empty, if q is not empty, right? And then we'll get it out. We say int current will equal to q dot poll. Okay. And city is going to be current 0, and dist will equal to current 1. If city is equal to target, we return dist immediately. If not, then we say for int next city. Right, because there's no back edge, so I think I can just go directly graph.get current. Okay, but just say next. I think it's fine. So we have a next city, right? And then we just put that in q.add new int. Okay, next city and dist plus 1. Don't even need this, right? Graph.get unlikely argument type in. Oh, my bad. City. Right, you get the next city, come out, and then you just find the first one. If it cannot, return -1. It should not reach here. Because you will not reach here. Definitely will not. Okay, and then shortest method. Oh, I forgot a target. Target is -1. Alright, so this will work, but I have worry that it will time out. I think I got this wrong. So this is the naive solution. Depending on how strict it is, I think. This is the naive solution where we perform a new BFS each time a new road is added to the graph. So this will run OMN time. Let's see how lucky we can be. And try it. Oh, I didn't test anything else. Oh, doesn't look good. I think it's gonna time out. Yep, this will time out. Cannot rely on this. We need something smarter. We need something definitely smarter. What do you think? Right, again, it's... Oh, maybe they are duplicates. Do we have duplicates here? Nope, it's not duplicates. It's still... I still want to go back to the previous idea, but it also feels you have to go through a lot of steps. Yeah, because you update it and then you have to update, right, everybody. Like whoever connect to them, you have to update. Whenever connect to them. And then once you do the last one, right, you say, okay, by doing this, we are making it faster. And then you're saying that I do this and make it faster. So whoever connect to you, they will become faster. But whoever connect to, like, just you have to. Or for one thing, once you do that, if you know the current shortest distance, once you do this bridge, you already know it's new shortest distance. That one is known. That one is good. Okay. And what if we don't update? What if we don't update, then we have the new one? Then how do we know that they are also good? I mean, you don't, right? You don't. So you have to go for everybody. That you see, this is the problem that I'm having. That you have to keep update. This is from their backfill. Would backfill be faster? I don't think so. All right, we need some hint. I need some hint. Are you calling my way is not efficient? Because it's already... I don't know, what does that mean, right? What does that mean? Maybe we can, I don't know, I really have no clue on this. Like, can we make it better? How do we make it better? You still have to go through the whole thing. I don't know. I'm using exactly the same method. Is there some places that I can do? Is there something I can do? I can have some information. Like, if there is something I can do. There is. You have a path, right? You added a new path, and after adding this new path, anything that's to the right of the path will not get affected, right? Will not get affected. So you basically can say, I will hold on, let me think again. So when you do a path, right? Everybody to the left will be affected. So you need to keep going until you hit this point, right? Until you hit this point, because everybody to the here, and then they, they will go. Then when you hit this one, right? When you hit this one, then you have kind of two ways to go. Because this is the old way and this is the new way, right? This is the new way. And once you have the new way, you get, okay, the shortest distance for this node. And when you reach a node that's beyond, that's actually not beyond, that's in between. And just beyond the starting, right? If you reach a node that's beyond the starting, then there's no change. So you shall just stop processing that, right? Because its shortest distance will not change. So basically, we'll get the shortest distance of the first part, right? And then we'll update them for sure. And once it goes beyond, then we just stop it because we know it's not going to make any difference compared to previous. Okay, so how are you going to make change to this? So each time I still go from here, but I record a DP. Okay, there's a DP array recording the shortest distance from each node towards the end. All right, that is fine. And as we go through the thing, every time we add, right, and then we go through here, and we will go to the next, to the next, to the next. So we just follow the same DFS things, right? Follow the same DFS thing, and BFS actually, right? We follow the same BFS thing. BFS thing. BFS thing. How do you follow the same BFS thing? Oh, if you want to do this, I think you need to reverse it. Because you need to keep a record of the number of steps, right? So from here is 0, and then basically I can go back here. So basically 1, 2, 3. So once we reach, so we go, but if you go reverse, yeah, I think it is just if you go beyond the new, if you go beyond the start of the thing, it's just not gonna work, because the only change is caused by adding this path, right? Adding this path, this path is what makes difference. So the only thing that can make this difference is everybody to the left that will, you know what, I do think we shall probably do a reverse style. You know, like who comes to you? Your parent, right? Your parent. So if we have a parent, then whenever we have a path, right? We have a path, so we can update that to 1, and then we go from here to go to its parent, right? To go to all the parent, right? And then each parent, its step will gets updated, right? Its step will get updated. So we have this current, then its step will get updated, and then its parent step will get updated. So we just go through the whole thing, and yeah, because currently every single time you have to go through the whole thing, but now you can make it like slightly faster, because again, like everything beyond this is useless, right? Everything beyond this is useless. Okay, so now I have kind of a solution 2. Let's try this. Okay, if this solution still doesn't work, then we're gonna call it, because I think it will take me at least another 20 minutes to write this up. By the time I finish writing, it's gonna be late. So this idea, it actually goes back to the previous idea. We have a dp, right? We have a new int n, and we have for int I 0. Yeah, we should actually say it one more time, right? So dpi is the minimum distance from I to n minus 1, right? I smaller than n and I plus plus. And what we do is dp I shall equal to n minus 1 minus I. Okay, so that's dp. And then what we need to have is, we're going to take a private void. Okay, so this is update. Yeah, we'll call it update. So we have dp, which is an int, right? We have a dp, and we need to know the start and end, right? Start, we need an end. So we have a start and we have an end. We say from start to end, right? So a new path is created from start to end, right? We have a new path. Update dp array for all the nodes for dp array for start, right? For start and all the nodes to the left, right? To the left. All the nodes that are parent, right? That are parents to st, because they are the ones that will make a difference. Right? If they do not come to this, if there's no way for them to reach, I mean, technically all of them has a way to reach, right? All of them, because you always have this. So all of them need to be updated. However, some of them will have extra jump to get there, right? Some of them will get extra jump to get there. So those extra jump need to be considered. Maybe I can use, I think this way BFS, DFS, they both work, right? They both work. They both work. Or maybe I can do, yeah, no, because I need to update every single one. If you don't update every single one, so by doing this, it's just we can save some steps. That's basically what we want to do. We want to save some steps. Okay, and I think I do need another thing. This is where we have a map, right, and a list of integer. This we'll call it parents. Okay, so update parent. We probably should update it before we call this function. This function should be, and what does this function do? This function says, because I need to go to my parent, right? So that will be the start, and that will be the end. So based on the current end, I need to update my start, right? Need to update my start. And if there's no change for me on the DP side, like basically it's not gonna make things better, then I don't propagate to my parent. But if it does make things better, I need to propagate to my parent. So basically it's gonna be like this. If, okay, DP and, okay, this is the shortest distance from and towards this, because I add from st to and, we say +1 is smaller than dpst, right? If it's smaller than that, then I say I need to update, right? Then I say dpst, actually let me do this, right? dpst will equal to dp and +1, and for int parent of parents.get st, right? Well, get its, we basically can call update dp, then be parent and st and parents, right? So we'll keep updating, else then we just don't do it, right? Else we don't do it. Okay, so this is actually not just that. I think I also need a map here. We can call it map, integer, list of integer, we call it parents. Okay, it's gonna be parent. So everybody need to have a parent, except from I, right? Because I does not have parent. So we say if I larger than 0. Parent, because I have the start to the end, and then we eventually a parent is going to be 0, the start will be 0, so I update the start, and then it does not have anything. Okay, so I can say it's get all default. Okay, get a default collections dot empty list. That should be that should do. And then here I can say this, and then we say parents dot put I new array list. Okay, and then parents dot get I dot add I minus 1. Okay, that's the start. And then we say for int queue of queries. Okay, and int u is q0. Actually, q is fine. I can just go q0 q1. All right, so we get a new one. So we need to update parents. The parents dot get the end, which is q1 dot add q0. Right, we add a parent, and then we call update dp. Start is gonna be q0, and is gonna be q1. Yeah, because I add this, right? Add this. The start parent does not change. The end parent changes, and then we do parents. So we do that. Okay, and we also need res new queries dot length. Okay, so this does not work because I need, oh my goodness, I smaller than queries dot length I plus. Now we can do this, q equal to queries I. If we want to do this, might as well just u and queries I 0, right? V queries I 1, and then all the so parents is gonna be v, have a new parents called u, and this is gonna be just u and I. Yeah, u and v. Once we're done, we say res I shall equal to dp0, and at the end we return res. Alright, so this is slightly different, and I think it can make it a little bit faster. Let's first see if it works. Maybe it also doesn't work, right? Maybe it also doesn't work. Alright, this one seems to be working. Okay, so this is the same idea. It's different. Okay, so we use the DP array to keep track of the shortest distance from any city from I to n minus 1. Okay, each time a new path is provided, the only nodes whose shortest distance, right, need to be updated are the ones to the left of queries J0, right? So by this update is faster, right? Should be faster than running BFS each time we BFS for each query, because we are not going through the entire, right? We're not going through the entire n. But we're still gonna call it OMN, but I do think this one shall be faster, and at least for this. Let's run it one more time. It's still slow because it says it's gonna be what, like 5 milliseconds, but I think it'll be faster than previous. Previous is just timeout, straightforward timeout. Yeah, this one is good. I think this is the way, right? Not sure, but it's pretty fast. It's pretty darn fast. All right. Okay, so now let's take a look. BFS. Dear Lord. Okay, yeah, I mean, you can definitely do something like this. Plus Q squared. Wait, is this not timeout? Are you BFS every single time? Oh my god, it's so long. BFS. Find number of edges the shortest path from 0. Okay, let's just see. From 0, visited. Oh, the trick is here. The trick is here. Ah, if it's visited, you don't do it again. Holy crap. I forgot about this completely. I mean, completely I forgot about the visited part. Yes. If it's been visited, then you don't do it, because, oh my god. All right, let's revive this. This could be our solution 3. All right, let's revive this. All right, so we need a visited. Gosh, dang it. I forgot about the visited. Okay, so we need an N. All right. And we need to have visited. Visited. Seen. Usually I call it seen. Ooh, you can do boolean. Let's do boolean. N. Okay. And Q add this seen 0 is true. Okay. To speed things up. If a node has been seen already, do not visit it again. I completely forgot about this. This is so bad. All right, so basically for this, well, we need to say if, right? If not seen, then we'll add to it, and then seen next, or equal to true. If it has been seen, then we don't do it. Oh, I'm pretty sure this one will work. Note that we use a seen array in the BFS to speed things up. How I did not see this before is quite embarrassing. Yeah, this is really embarrassing that you didn't see this one. All right, let's try it. I believe this is the key. Oh, that's fine. That's fine. Just do it this way. It's okay. Yup. It's slower. Yeah, it's slower, but damn it, it works. Yeah, it works. It works, but I mean, the other one is way faster. Way faster. So it's q times n plus q squared. I mean, mn for sure. Why do you have to do q squared? Oh, they use this. I have no clue. Because you go through Q times, right? Each Q times this shortest distance. Well, it depends on how many paths. How many paths do we get? So initially it's n path, right? And then we do m plus 1, m plus 2, all the way to m plus q. Yep. That actually makes sense. Okay, yeah, that actually makes sense. Recursive DP. I mean, I am doing DP. I am doing DP in this. I think we did hit the jackpot on this one. This is the jackpot. It's the fastest. Pretty straightforward, honestly. You just need to keep track of the parents. All right, that will be it. Good question. 1 hour. Damn it. All right, I will see you guys tomorrow. Adios.